The last among the types of probability distribution is the Poisson distribution, and this is associated to the Poisson random variable, which is defined from a Poisson experiment. A Poisson experiment yields numerical values of a random variable x, which represents the number of outcomes occurring during a given time interval or in a specified region or location. And these are called Poisson experiments. Examples of Poisson experiments would be counting the number of typhoons that will enter the Philippine area of responsibility in a given month. So in that example, the specified location or region is the Philippine area of responsibility and the time interval is monthly. So for the Poisson distribution, the probability mass function is given by the formula P of x equals the natural exponential number e, which is raised to negative mu times mu raised to x over x factorial. So x here is the random variable or the Poisson random variable, while the mu is the average number of occurrences in a given time interval or specified region. So for example, if we say that the average number of typhoons that enter the Philippine area of responsibility per month is 2, then that means mu equals 2. And that will be fixed for this particular formula. Now, for the Poisson distribution, the possible values of x would range from 0, 1, and 2, and this is continuous without end. Because in Poisson distributions, we don't know how many occurrences of a phenomena will happen in a specified region or in a given time interval. So for example, if we say that the number of typhoons that will enter the Philippine area of responsibility for the month of November is 3, then we are not sure about that because it's possible that there will be 4 or 5 or 6 or 7 typhoons that will enter the Philippine area of responsibility in a given month. Okay, so that's why for the Poisson distribution, the lowest possible values of x is 0, but the highest possible values of x is unknown. Now, for the mean and the variance of the Poisson random variable, no, the mean is always given, no, in a Poisson distribution. So the average number is always given and it is mu, while the variance of the random variable x is also equal to the value of mu. So the standard deviation sigma sub x is equal to the square root of the mean mu. Okay, let's have an example. On average, a certain intersection results in 3 traffic accidents per month. Okay, so in this scenario, the average number of traffic accidents is being counted. Okay, or the number of traffic accidents is being counted. And the average per month is 3. And the location that we're talking about is a certain intersection. So in this case, now we're going to use the Poisson distribution because we're counting the number of traffic accidents that will happen in a specified location or time interval. So in this case, yung x natin will range from 0, 1, 2, and so on. Okay, so the question is, what is the probability that for any given month at this intersection, exactly 5 accidents will occur? So which means we're looking for the probability that x is equal to 5, which corresponds to small p of 5. And from our formula, if we have p of 5, that means we're using x equals 5, which means that there are exactly 5 accidents that will occur. So p of 5 is e raised to negative mu, which is 3, times mu raised to x, which is 5, over 5 factorial. Okay, and this is equal to 0.1008. Now for letter B, we're tasked to get the probability that for any given month at this intersection, there will be less than 3 accidents that will occur. So for letter B, we're supposed to find the probability that the random variable x is less than 3. So which means we're looking for the probability of x equals 0 plus the probability that x equals 1 plus the probability that x is equal to 2. So in this case, the p of 0 plus p of 1 plus p of 2, we get p of 0 as e raised to negative 3 times 3 raised to 0 over 0 factorial plus e raised to negative 3 times 3 raised to 1 over 1 factorial plus e raised to negative 3 times 3 squared over 2 factorial. So using your calculators and adding all of these quantities, we shall get 0.4232. Okay? Now, for the third example, for letter C, we're supposed to find the probability that for any given month at this intersection, at least 2 accidents will occur. So if we are tasked to find at least 2 accidents will occur, that means we're getting the probability that x is greater than or equal to 2. However, the problem in Poisson distribution is that the possible values of x um, is unending and we don't know the highest possible value of x. So if we're going to use this formula, p of 2 plus p of 3 plus p of 4 and so on and so forth, then we're not going to end our solution. So in this case, if we're getting the probability that x is greater than or equal, or whenever x is greater than, then we have to use the complement of x is greater than or equal to 2. And the complement of this will be 1 minus the probability that x is less than 2, which means that we're looking for 1 minus the sum of p of 0 and p of 1. So this quantity here is actually the same as p of 2 plus p of 3 plus p of 4 and so on and so forth. Okay, so we get 1 minus p of 0 is e to the negative 3 times 3 raised to 0 over 0 factorial plus e raised to negative 3 times 3 raised to 1 over 1 factorial. And this quantity is equal to 0.8009. Now for item D, the variance sigma sub x squared is actually equal to the mean mu, which is 3, while the standard deviation is just the square root of the mean mu, which is square root of 3. Now for our next example, a certain area of the eastern United States is on average hit by 6 hurricanes a year. So the location that we're using in this Poisson experiment is the eastern or the part of eastern United States. And the time interval that we're using is yearly or every year. And it is said that the average number of hurricanes a year is equal to 6. So this thing will be our mu. Now, our question is find the probability that for a given year, the area will be hit by um, 6 to 8 hurricanes. Okay, so if we want to find this thing, then we should get the probability that x is from 6 up to 8, which is p of 6 plus p of 7 plus p of 8. Okay, so for letter A, p of 6 is e raised to mu, which is negative 6, times mu, which is 6, raised to x, which is 6, over x factorial. Now, for x equals 7, we have e raised to negative 6 times 6 raised to 7 over 7 factorial. And whenever x is equal to 8, then we have e raised to negative 6 times 6 raised to 8 over 8 factorial. And this thing is actually equal to 0.4016. Now for letter B, for the mean and the variance, the mean mu is mu sub x equals 6 hurricanes a year, while the variance is sigma sub x squared equals also 6. Now for letter C, we're supposed to find the probability that there would be fewer than 4 hurricanes in 2 years. However, in our problem here, the given average is per year. No, it is 6 hurricanes per year. So if the problem would involve a different time period, then we have to adjust the value of the average. So if in a year the average is 6 hurricanes, then that implies that in 2 years the average will be 12 hurricanes. Okay, so for letter C, we want to find out that there would be fewer than 4 hurricanes. So that's P, or the probability that X is less than 4. But take note that we're using a value of the average, which is 12, because the time interval is 2 years. So here we have P of 0 plus P of 1 plus P of 2 plus P of 3. So when X is equal to 0, we have E raised to negative 12 times 12 raised to 0 over 0 factorial. And whenever we have P of 1, we have e to the negative 12 times 12 raised to 1 over 1 factorial. For P of 2, we have e raised to negative 12 times 12 raised to 2 over 2 factorial. And lastly, for P of 3, we have e to the negative 12 times 12 raised to 3 over 3 factorial. And this thing, no, when you use your calculator, is 0.0023. Okay, so this ends our discussion of chapter 7, which involves the special types of probability distribution enumerated as the binomial distribution, hypergeometric distribution, and this topic, which is the Poisson distribution.